and I'm super excited and also super nervous to the same extent to be here. This is my first DroidCon conference, and thank you for having me. So my talk for today is going to be about the lessons we learned while porting our in-house game engine called Roloengine from iOS to Android. I'll be using our first Android game, Flick Tennis, as a case study. You can think of this talk as a collection of tips and tricks, do's and don'ts, lessons that we have learned, some the hard way, while during our porting process. So, Roloengine saw its humble beginnings with our first game in Touch Squash, which was released in 2009. It was a simple game which involved, well, as most of you might have seen squash, it involves two rackets and a ball. Roloengine saw an organic growth, and we expanded it and slowly added more features. And in 2010, we released Super Badminton, which featured 3D models, animations, and a simple AI. It used a virtual control pad. In 2011, we revamped our systems. We revamped our 3D model rendering system, our animation system. We included a custom physics engine, and we released Flick Tennis. In 2013, we see the next gen version of Roloengine, which, along with a better 3D rendering, also used motion gestures to control your game. So essentially you could use your phone as a tennis racket and swipe around, and you could see the corresponding actions being taken on your TV screen if you had an Apple TV. Our first foray into the Android market was Flick Tennis, which was released in June 2013, and we do have more games coming out in the pipeline. So what is Roloengine? Roloengine saw its beginning in iOS. Hence, it was a custom in-house engine specifically geared towards racket sports, which was written in Objective-C. It used Opengl ES 2.0 for rendering. Opengl is the equivalent for audio, which gives you 3D audio rendering as well. We had a custom physics engine which we use for some of our advanced features for Flick Tennis and the rest of the games. We had our own animation engine for skeletal animations, and for optimized asset pipeline, we built our own proprietary format which we used for assets such as models and animations. When we first decided to port our games to Android, in the very beginning itself, we hit a huge vital decision node. Those who have attended Chris's talk would probably have a better idea about this, but we had decided that C++ and NDK is the best way to go about porting our game from iOS to Android. However, at that juncture, we had two major options that we could do. One was to go completely native by using the C++ NDK. Android provides you with what is called as native activity, which lets you bypass the entire or most of the entire Dalvik VM, and you could set up your entire application in C++. And that gives you much control when it comes to memory management, and it also arguably was faster for some of the older devices. But with going completely native, there were a few cons as well, one of which was that you no longer had the support of the excellent UI system that Android supports. Also, the NDK does not, as of this moment, expose all the APIs that you can access through Java. Whereas, if you look at the second approach, what we would do is we would utilize each system to its strength. We would use Java along with the Android UI to leverage the strong and rich look and feel of Android, whereas we could use C and C++ to leverage the bare metal performance that we could get. And this had an advantage where we could use each language's API easily. However, it did have a slight hassle of communication with the UI. So, our component set for Roloengine Android version was ported in such a way that we maintained API compatibility and we made as minimal changes as possible to also give it an almost cross-platform nature. We use C++ as our primary language for the game rendering, animations and the game logic, whereas we use Java for UI. OpenGL was ported more or less consistently from iOS to Android. In order to keep API compatibility, we used software implementation of Opengl, and our physics engine, animation engine, and the asset formats were ported equally easily. So, looking at the major component that was important when it comes to a 3D game is the rendering engine. From Android 2.3 and onwards, what you see is that OpenGL ES 2.0 has a very good and competent implementation, and we could easily port our game from iOS to Android. However, those who are acquainted with OpenGL and have used a fixed pipeline from 1.0 or 1.0, there's a word of caution. Do not try to mix 1.0 and 2.0 API calls. It is a recipe for disaster. It is quite possible that it might work on some devices, and on some devices the best case scenario would be a state corruption. If it is necessary, I would recommend that you create your own versions of the fixed pipeline mechanisms such as GL begin or GL end, GL push matrix or GL pop matrix. Coming back to our original dilemma of using a completely native implementation or going the hybrid way, what you see here is the native way of setting up the OpenGL context. The OpenGL context is one of the most important setups that you need to do before you actually can use OpenGL. And what I hope to do with this and the next slide is to show you that it's not easy peasy. Although it's a one-time setup, it's still additional code that you need to manage and handle. And all of this is just to set up the OpenGL context. Whereas we decided to go another way. We leverage the Java APIs. GL Surface View is an excellent class which sets up the context automatically and gives you the default context, which works for most cases. All you need to do is pass on a simple GL renderer. What you see here is the GL renderer class, where we use JNI, which is the Java native interface, to make calls to the C and C++ code. The corresponding C++ code looks something like this, where you can hijack the rendering thread, and from here it would be the entry point for your game. This would be your game logic. This would be your game engine per se. Some of the problems that we've faced, and what I would like to impart to you is that always make sure that all your OpenGL calls are on the render thread. That is what you're seeing is one of the most common case for rendering glitches that you see. For example, if you were to use gesture recognizer for getting touch input data, Android actually gives it to you on a separate thread. If you immediately consume that data and start rendering based on that, what would happen is, at the best case, you would end up with corrupting your state. At the worst case, it will just crash your application. Some of the older devices had a non-optimal combination of garbage collectors and GIT, which is the just-in-time compilers. What that would lead to is significant pauses when the garbage collector ran, and that means flickering FPS. That means possible problems to your timing issues to your physics engine, to your animation engine. So as a rule of thumb, avoid touching or creating any objects during your update loop. OpenGL rendering or rendering in general is a battery intensive task. It would be very wise of you to actually pause your rendering thread when your application is sent into background. Otherwise, it will just eat up your battery and your client would just uninstall your application. Next, we have the audio section. Android provides two Java APIs, Sound Pool and Media Pool. These support 2D audios, and it provides you one native API, OpenSL ES. The Java APIs, along with being 2D, also have significant latencies when it comes to older devices. And while OpenSL works perfectly, it has a very ugly, I would say, and a convoluted API. And one of our aims was to keep API compatibility, for which we went with a software solution of Opengl. It maintains API compatibility, but at the same time, it uses OpenSL as its backend. So we can have our cake and eat it too. Since C++ was a language of choice, and it being bare in some regions from a standard library point of view, we had to use certain libraries to make our jobs easier. One of which was Boost. Boost is a heavyweight when it comes to libraries. However, it was quite easy, surprisingly, to get it to build for Android. There's an active project which helps you set up and build Boost, selectively build Boost for Android devices. It also supports ARM and the ARMs and Intel architectures. The two most important libraries from Boost that we used was BoostBind and Boost.io, and smart pointers definitely helped. For XML parsing, we used TinyXML2. It was a very lightweight, but at the same time powerful API. For loading our texture data, we used a combination of libpng and libzips. Last but not least, what we have is the Android UI. Android is notoriously stingy when it comes to memory. The default or the standard Java heap that you would get is around 16 MBs. Certain devices take up to 24, possibly 32 MBs. But this is the case for devices which support 1 GB, 2 GB of RAM. It is quite easy for you to load up multiple bitmaps, large bitmaps, and run out of heap space. The solution for such a problem is to fiddle around with your bitmap factory options. There are two options which help the most. One is inpurgeable, which ensures that your bitmap releases its memory as soon as it is done with the rendering. Is input shareable is another one which ensures that your input stream is shared across multiple bitmap loads. This does have a disadvantage of adding in extra loading time for your images, but it is much better than the alternative of your application just crashing because it ran out of memory. Two tips for UI. One would be that from the very beginning itself, consider making multiple layouts for different classes of screen sizes. It is almost impossible to use the same one across multiple classes and get the same look and feel. The stock Android fonts and type spaces are very sparse and disappointing. It would be nice if and quite useful if you figure out your own fonts and set them up. Thank you. Any questions? Yes, please.
Hello. Yeah. Hi, I'm Rajat.
Hi.
How do you solve the problem of text rendering on Android? Did you just use bitmaps for the text and then use it, or did you have your own text rendering library?
So we used a hack, I would say. For most of our text rendering, we actually had UI placed on top of the GL surface. Okay, so we used the Android UI for text. And because we were aware of the pixelization issue, and it's not an easy problem to solve. Okay. So we took an easy way out and used the UI to render text.
So you just placed the text view over it and then.
Correct.
Okay.
Correct. But so what you could use is a transparent relative layout and put in the views that you want to show. A text view, for example, and it could sit on top of your OpenGL view.
But then the problem with translation of coordinates from the GL space to the text view space.
Yes, that's quite correct. This is more helpful when you have static positions.
Okay. Thank you.
Hi Manish.
Hi.
I'm Sandeep. I had a question about the bitmap problem you were saying, because you said you had some trouble with memory management, correct?
Correct.
So what kind of reference were you using when we're pointing to the bitmap over there? We got multiple references which came in Java 2.0.
Uh-huh. Right, you're talking about the
have you ever heard of a phantom reference? Weak references?
Weak references versus...
Yeah, so you can use a phantom reference. It will return you a pointer.
Uh-huh.
So once that's filled, it will give out an error. That's the only way to see the garbage collection has been requested on that particular object. Probably you can use it and your problem will be solved.
We did try this, but what we saw was we got inconsistent results. So the GC was non-deterministic when it came to collecting up the spare bitmap heap space that was used. So we would see this issue sometimes, like maybe 1 in 20. But that was still an issue for us.
Okay. No, because we generally have come across these issues I'm a software engineer, but we come across issues like this in Tomcat long back in 2003, and we had large text files the same way because of PDFs, and we used to use iText. We just resolved those problems using a phantom reference, and we could figure out the garbage collection has been kicked in, and it's out of memory, and then have a strategy for that using our flyweight design pattern. The way the string objects are used in our JVM.
Okay.
Maybe a strategy like that would work for you.
This might have worked for the JVM GC that comes along with it, but the Dalvik GC that's part of the Android probably works in a different way. Plus, you also have to compensate for the fact that there are so many Android versions out there with different GCs with different implementations of GCs. So, I am not sure if this is a solution which would work for all devices, especially for some of the older ones, which is where we saw the issue.
All right, thank you.